Hello students, let's proceed for the next topic where we are going to study about the pressure on concave side will always be greater than pressure on convex side. Okay, so I have drawn three diagrams. First is a plane surface, second one is a convex surface, third one is a concave surface, and we are supposed to understand whether pressure on concave side will always be greater or not. First of all, let me tell you how to judge whether we are on concave side or on convex side. So imagine that you are always standing outside, okay, upside or outside. So from this side, when you see this kind of shape, okay, obviously this will be a convex for you. When you are standing over here, this kind of shape will be called as a concave shape for you. And this is obviously a flat one. Okay. Now I have assumed 2 points, A and B. One is above the surface, another one is below the surface. Let me tell you, these 2 points are very close to each other. Okay, so they are not contributing much difference in pressure. One is above, another is below. We can consider that they are very close to the surface. On point A, the pressure acting is the atmospheric pressure. Okay, so force on point A is obviously due to the atmosphere. Correct. So I will be writing here the force acting is Fa. This is due to atmosphere. You know the concept of surface tension. This surface is acting like an elastic membrane which is being stretched. Okay, so there will be forces due to surface tension on the molecules on in the surface film that I'll be showing over here. Let us consider here we have one force FB. Here also we have one more force FB. What are these forces doing? They are trying to stretch this membrane. Okay, and this is what is surface tension tangential forces. If you observe that these two forces are equal and opposite, so what they are doing, they are cancelling it. Clear? So if I ask you what is the force on B, then the answer will be it is same as A. So what do we conclude from this is the forces on A and B are the same. Hence, pressure on A as well as pressure on B will also be considered as same. So I will write pressure at point A is equal to pressure at point B. So in case of a plane surface, pressures on point inside the liquid as well as outside the liquid has to be considered same. With the condition they should be quite nearer to the surface. Let's move on to the second case. I can see a concave surface. Again, I will be taking 2 points. First point will be over here, A. Second point will be over here, which is B. Okay. Now, this time again at A, the force will be due to atmosphere. So I will be writing F A. But at B, please be careful. This time the forces are trying to pull it inside the liquid. Okay, it has form a convex meniscus. So force B will be something like this. FB. Here also the forces will be something like this. FB. Okay, trying to pull it down. Is it understood? Now, these two forces, if I want to draw a resultant of these two forces, or resultant of these two forces, then it will be coming something like this. Ft. This is the resultant force, okay, of this two. Observe at point B, the forces first of all due to A as well as Ft, they are in the same direction, so they get added. So due to these two forces, I can say that more force is exerted on point B as compared to point A. So point B is under more pressure due to addition of these forces. So what I can write? Pressure at B is greater than pressure at A. And we know B side will be called as a concave side and A side will be called as a convex. So I can write pressure on concave is greater than pressure on convex. So here we prove this part. Let's move on to the third case. Here again the same way, I will be taking 2 points. Point A, here is point B. Clear? Again at A, forces will be due to atmospheric pressure. So I will be writing over here Fe. This time the meniscus is going up. So forces on B are acting in upward direction. So I will be showing that way. This is the forces which is going in this way. This is the forces which is going this way. Have you understood? Now, if I want to draw the resultant of this two force, obviously it will be shown this way in upward direction. So I will be showing something like this. This is the resultant. Okay. Now observe point B. What has happened? Two forces are acting equal. Sorry, two forces are in opposite direction. Here it was getting added up, but here instead of getting added up, it will get reduced because of opposite direction of both the forces. So what I can conclude that pressure at B this time would be less when compared to pressure at A, because the force on B side is getting reduced due to this Ft acting in opposite direction when compared to Fa. Okay, so I can write over here this time Pa will be greater than Pb, and you know A side is nothing but concave, B side is nothing but convex. So here also we conclude that pressure on concave side is greater than pressure on convex side. Okay students, let's move on to the next derivation, which is finding out the formula for excess pressure inside a liquid drop. The last formula that we will come across is Pi minus Po is equal to 2 into T upon R. This will be our last formula. First of all, understand this. This is pressure inside minus pressure outside, which will be equal to 2 into surface tension divided by the radius of that liquid drop. Okay. So I have drawn a liquid drop over here. The radius of this drop is denoted by R. Okay. Now try to understand, pressure inside will be more or pressure outside will be more. I have always told you that you are supposed to assume yourself standing outside. So if you are standing outside over here or here, this surface will be in front of you. I hope you understand. This kind of surface will be in front of you. So in front of you, you have convex surface. Correct? And we have already studied that pressure on concave side is more than pressure on convex side. So this becomes convex side and inside becomes concave. So what I can conclude, pressure inside is more because it is concave side, and pressure outside is less because it is convex. Hence pressure inside minus pressure outside. Have you understood this? Now let's start the derivation. In this case, what we are going to do, we are going to give a small displacement to increase its radius by a very small amount, which will be denoted as delta R. So this is the increase in radius delta R. So definitely area will change. So let's try to find out the change in area. Initial area A1, which I'll be writing, it should be surface area. So surface area formula, you know, it is 4 pi r square. This is initial surface area. A2 will be your final surface area. 4 pi, radius has changed. It is r plus delta r the whole square. Now I'll subtract these two areas, so I'll get the increase in surface area. So A2 minus A1 will be equal to 4 pi A2. I'll elaborate this. R square plus 2r delta r plus delta r square. Okay, I have applied the formula of a plus b the whole square minus this term, which is 4 pi r square. Okay, now our next step will be just open this. So this will give me 4 pi r square plus 8 pi r delta r plus 4 pi delta r square, and then minus 4 pi r square. So one thing you can observe that this terms can get cancelled. Okay. Next thing, delta r is considered as very small, very small. Okay, infinitesimally small. So if you square a very small term, okay, then it can be neglected. So I can write here delta r is very small. Okay, so therefore delta r square is almost considered as 0. Clear with this? So here this terms can also be considered as 0, neglected. So the change in area, that is denoted by dA. dA is the change in area. We are left with only 8 pi r into delta r. So here I write this is dA. So we have arrived to the change in surface area. Now let's move on to the next part, which is to find out the work done. Okay, obviously we are pulling this, okay, we are increasing the radius, so some amount of work has to be done. So work done formula, you know, it is force into the displacement. Displacement here is nothing but equal to delta r. So force into delta r. Now it's time to find out the formula of this force. Okay, we know the formula that pressure is equal to force upon area. Okay, but here this pressure will be excess pressure. This force will also be excess force. So therefore, I will be writing excess force, which is F, is equal to excess pressure, that is Pi minus Po, excess pressure into this area. Clear? So therefore we will get Pi minus Po into area formula, we will be taking 4 pi r square. So we got the formula of excess force. This we can substitute over here. So therefore I can write dW is equal to, instead of this, Pi minus Po into 4 pi r square into this delta r. Okay, I substituted this over here and we got this part. Now recollect the derivation of surface energy. Okay, surface energy derivation, we had derived the work done, which is equal to surface tension into change in surface area. So I'll be writing that again. Since we know that dW can also be written as T into dA. Correct? This we have already covered in our previous lectures. dA, I will be substituting from this part. Okay, so this will be written as T into dA is 8 pi r delta r. This is your dW. Now I name some equations for avoiding confusion. Let us consider this is our equation number equation B. Let us consider this as equation A. Okay, and when you observe equation A and B, the LHS is same, work done. So we can equate RHS also. So I will be writing from A and B. Therefore, I will be writing Pi minus Po into 4 pi r square delta r, which is equal to P into 8 pi r delta r. Okay, now let's see what all things can get cancelled. Pi got cancelled, delta r got cancelled, one r term can get cancelled, one r is left out. This is 4 ones are, this is 4 twos are. Okay, so see what all things we are left with. On LHS we have Pi minus Po into, here we are left with r is equal to, we are left with 2t. Okay, so 2t. So therefore our final answer comes as Pi minus Po is equal to 2t by r. So you can very well see this answer must be matching with the formula that we have written at the start of this derivation. This completes the derivation of excess pressure inside a liquid rock. Let me tell you, this derivation is also related with one scientist, which is called as Laplace's law. This is also called as Laplace's law for spherical membrane. This was all for liquid rock. Now, in case of soap bubble, instead of liquid rock, if we are taking a soap bubble, then you know that for soap bubble there are two surfaces in contact. One is inner, another one is outer. So, because of that, what is going to happen? Instead of 8, we will have to consider 16. Okay, double, two surfaces in contact. And because of 16 over here, when you solve over here, 4 ones are and 4 fours are, I'll be getting 16. So here instead of 2, 4 will come and our last answer will change. Pi minus Po will be written as 4T upon R in case of soap bubble. So this completes the major derivation. You can have a look at this. Okay, students, let's move on to our next topic, which is capillarity. Very interesting topic, quite easy. First, I'll explain you what is capillarity. I've written the definition on the board, but before going to the definition, I'll just tell you a simple example. Let's say if you have a glass beaker, okay, which you can hold in your hand, fill it with water. Take a capillary tube. Capillary tube, everyone must have seen in your chemistry lab. Okay, very thin tube which you can hold it, and even if you apply pressure, might break also. That is the thin capillary tube, and dip it inside that beaker. What will be your observation? You will observe that liquid rises in that capillary tube. Okay, whatever the level is there in the beaker, above that level, the water will rise in the capillary. Correct? Now, instead of water, if you had taken mercury, then your observation would be different. Instead of rising, the mercury will drop. The level of mercury will drop inside the capillary tube. So this is something which is happening naturally. It's a phenomenon. Okay, and this phenomenon is what is called as capillarity. So I have written the definition: the phenomenon of rise or fall of a liquid inside a capillary tube when you dip it in the liquid is what is called as capillarity. Now, capillarity you can observe in our day-to-day life at not many places. I have listed 4 of them. First of all, you can see this is the best one. Everyone must have experienced this in their life. A blotting paper will absorb the ink. Okay, so if you put a blotting paper on ink drop, you will observe that major part of the blotting paper will be covered with ink. Similarly, if water is dropped on the floor and if you put a cloth over it, then you observe that cloth is taking up all the water, and some part of the cloth is seen as filled with water. Next important one, you can see that oil will rise in the wick of the lamp. Now, what is wick? What is lamp? In Hindi, we call it as diya or bati. Correct? So, in that also you can see that oil is coming up, and that is how we are able to light those diyas during Diwali. Okay? And one more thing, it is about sap and water. You know that water is absorbed by the roots, but that water is reaching till the top part. So that is also happening due to this phenomenon called as capillarity. Sap, biology students must be aware, it is other than water. Plants have some cell fluids also apart from water. So that all things are included under sap. So that is also being carried up till the topmost part of the tree. So going up, I hope you understand, this is rising of liquid, and that all things come under capillarity. Okay. Next, we have to understand the reason also. Okay, we have seen this phenomenon that okay, water rises, mercury drops, but we have to understand the logic behind it. What is the physics behind that? We enjoy rainbow, we see sky blue in color, we see sky reddish orange during sunrise, during sunset. But in physics, we understand the reason behind it, why it is so. Correct? So similarly, here also we observe something, but we have to understand what is the physics behind that. So let's move on to these two diagrams. Okay, to understand this, why there is capillary rise, we should be aware of one simple property of liquid, that liquid will always flow from high pressure region to low pressure region. It is very easy to understand. If there is a stove, okay, this is the point of high height, this is the point of low height. So definitely fluid or water or anything is obviously going to fall from high to low. Correct? Same way, wherever the pressure is more, from that side, the liquid will go to the place where pressure is low. Clear? So this thing you should keep it in your mind, and let's move on to this. What I have shown is a beaker, capillary tube dipped in it, okay, and this liquid is nothing but water, because we are going to observe capillary rise. Now here you will require that concept of convex and concave. Pressure on concave side is greater and pressure on convex side is less. Whereas along the plane surface, pressure inside as well as pressure outside remains same. Okay. So here this is your plane surface. Okay. And C point is outside, D point is inside. So I can write pressure at C is equal to pressure at D. Correct? Check this A and B. Now, which one is concave side? I have told you, you should imagine you are watching this from the top. Okay, so this part, okay, this becomes your concave side. So I can write pressure at A is greater than pressure at B. A side is concave, so pressure is more on that side. Now observe this point A and C. Those both points are open to the atmosphere. Correct or not? This is open to the atmosphere. This one is also open to the atmosphere. So on both points A and C, atmospheric pressure is acting. So pressure is same at A as well as at C. So I can write pressure at A is equal to pressure at C. Now from this, what we conclude, let us assume this with the help of some values. Pressure at A, let's say 100. Pressure at B should be less, let's say 70. Pressure at A is 100, then C will also be 100. Pressure at C is 100, so at B is also 100. So what we conclude, this is 100 and this is 70. So if I ask you, pressure at D is more compared to D, or is it less compared to D? You know the answer, 170. So I can finally write pressure at D is greater than pressure at D. So try to understand, here pressure is more. On this side, the pressure is more. Whereas on this side, the pressure is less. Correct? So what I told you, liquids will flow from more pressure region to the lesser pressure region. So that is how the liquid will flow from B to point B, like this. And that is how the liquid rises. And it rises till that point such that D and B pressure becomes equal. I repeat this again. Pressure at D is more, pressure at D is less. There's a very simple property that liquid flow from higher pressure region to lower pressure region, and hence liquid will flow from D towards B, and that is how the water rises in the capillary till that much height, so that these two pressures are again made equal. Okay, now let's move on to the next part, capillary fall. In case of mercury, this liquid we are considering is mercury. Same logic, okay, just the meniscus has changed. Clear? This is a plane surface, so I can again write PC is equal to PD. It's a plane surface. Inside point as well as outside point has same pressure. Clear with this? Observe this part. Now concave side is on B, whereas convex side is on A. So pressure on concave, that is B, will be greater than pressure at A. Clear with this? Observe A and C. Again, they are open to the atmosphere. So I can write at A as well as at C. Atmospheric pressure is acting, so pressures are also same. Again, try to understand with this with the help of some values. Okay, let us consider this is 100. So this also becomes 100. PC is 100, so D also becomes 100. So A is 100, definitely B should be more than 100. Let's say it is 120. So when you compare D and B, this is 120 and this is 100. So I can write pressure at B is greater than pressure at D. So this time here I will write the pressure is more, and here I will write the pressure is less. And you know the property that liquid will flow from more pressure region to less pressure region. This time the flow of liquid will be from B towards D. I hope you understand. The flow will be like this. And since the liquid is flowing like this level will drop. And it will drop to such an extent so that these pressures are again becoming equal. So this is the physics behind capillary rise as well as capillary fall. Okay students, let's move on to our next derivation, which is expression for capillary rise or fall. So whenever the height of that liquid column which will rise in the capillary, that derivation we are going to do. The last answer that will come will be H equal to 2t cos theta r rho g. T is the surface tension, theta is the angle of contact, r radius of this capillary tube, rho density of this liquid, and g, you know, acceleration due to gravity. Okay. Before moving to this derivation, let's have a quick concept about coin dipped in a liquid. Okay. If a coin is dipped in a liquid, obviously surface tension will act. Clear? Now coin is not a hollow part, it is a solid. This whole part is a solid. So when water is in contact with this circumference, what will be the formula of surface tension? We know basic formula of surface tension is equal to T is equal to F upon L. L is the length along which the tangential forces act. Now in this case, the tangential forces are going to act along the circumference of the coin, like this. Here, 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 everywhere. Correct? This way tangential forces will be acting along the circumference. So the formula will get modified. T will be equal to F divided by 2 pi r. R is the radius of the coin. Similarly, F formula can be written as T into 2 pi r. So this concept we are similarly going to use in this derivation. So hence I had explained you this. Right now I am rubbing this part. Okay, just keep this thing in your mind. Okay, so now let's understand that this liquid is considered as water because there is a rising capillary tube. Okay, and the meniscus you can observe it is concave. So for concave meniscus, first let's show the angle of contact. Okay, so I'll be drawing a tangent like this. Clear? And here I'll get the angle of contact, theta. Correct? Now you know that for concave meniscus, okay, outside and convex inside, the forces are going to be acting like this, okay, which is going to in upward direction. So I am going to show that force over here in upward direction. This is the force due to surface tension, as well as I can show force on this side also. And this is a capillary tube, it is circular in form. So this forces will be acting along the whole circumference. Is it clear or not? Now let me show this theta over here also. Opposite angles. I hope you understand this. Okay. So now our next part will be to find out the component of this force due to surface tension, which is causing the liquid to rise. Okay, I repeat this. We are going to find the component of force due to surface tension, which is causing the liquid to rise. Okay, so for that, obviously, we will have to resolve this into two parts, sine theta as well as cos theta. So we know that the component which makes an angle will be given as cos theta. So this side ft is making an angle with this side. So this will be written as ft cos theta, and this side perpendicular to it will be written as ft sin theta. Have you understood? So this is the component, upward component, which is causing the liquid to rise. Is it clear? Now you know that this is going to be a circumference, so it's something like this. Correct? So this ft is not only going to act at this single point, it is going to act along the whole circumference. Is it clear? Now let's get back to that simple concept of point. What I had written, T is equal to F upon L, but instead of L, circumference, I'll have to write as 2 pi r. Instead of F, in this derivation we have Ft, so therefore Ft will be written as T into 2 pi r. Is it clear? Now this liquid is in equilibrium, it is not moving. So upward forces needs to be balanced by downward forces. Upward forces I can see. What about downward force? Downward force here, it is nothing but the weight of that liquid in the capillary tube. This much weight. So weight of this liquid, we know the simple formula mg. So what we are going to do next is upward force will be equated to downward force. Correct? So for finding the downward force, that is the weight mg. First of all, let's find this downward force. Okay. So weight of the liquid column we will be finding first, which will be m into g. Correct? Mass formula, you know, it is density into volume, because density is mass upon volume. So I will be writing density into volume into g. I hope it is clear so far. We need to find the volume now. Volume of this much part. Clear with this? Now just understand, volume of this is nothing but the volume of a cylinder. See, check. I am just drawing a cylinder. Can you see? I have just drawn a cylinder. And volume formula, everybody knows that it is area into height. Area into height. This is that height. Okay, this much part is the cylinder, area into height. Area, if we need to find, it is a circle. So area formula will be pi r square. So this will be written as pi r square into h. Area pi r square into h. So formula of this volume can be substituted over here. So therefore, weight is equal to rho into pi r square into h into g. Is it understood? Now this weight is nothing but our downward force. What about upward force? Upward force is nothing but Ft cos theta. So let me write over here, our upward force is equal to Ft cos theta, which can also be written as Ft value is T into 2 pi r. Okay, and then we have cos theta. We got our upward force. This is our downward force. Let me write over here. This is our downward force. Okay, now let's equate this two. Upward force T into 2 pi r into cos theta is equal to downward force will be equal to rho into pi r square into h into g. Okay, now let's see what all things can get cancelled. I can see pi got cancelled. One r term can get cancelled. One r is left out. So we are having t into cos theta. 2 is also there. Is equal to rho into r into h into g. We need to find the formula of h. Just isolate h over there. So h will be equal to 2t cos theta. This three terms will get divided, rho, r and g. So you can just very well check whether this is matching or not. H is equal to 2t cos theta, r rho g. Okay. From this, if you want to find the surface tension, like if you have the height, you might measure the height with a scale, and if you want to find the surface tension of the liquid, then the formula will become P is equal to, this will remain as it is, rho r h g, and 2 cos theta will be divided over here. So this completes the derivation for capillary rise or fall.